welcome to another math club talk. Today we have Korou Khundrakpam. He is a B.Math second year over here, and he will be talking about prime number theorems, one of the elementary proofs. Over to you.
Thank you everyone. So welcome to today's math club talk. Today's topic, as I read, is an elementary proof of the prime number theorem. And the overall abstract of this talk is to use Chebyshev's theorem and certain results from analytic number theory to eventually go over how Selberg gave us an elementary proof of the prime number theorem. Now the word elementary does not mean easy. The proof itself is full of subtle arguments and certain tricks that Selberg used so as to prove it in an elementary manner. So we begin by stating the prime number theorem. So prime number theorem begins with the function pi of x, which is basically the number of prime numbers which are less than or equal to x, which is defined as follows. Now, to study the prime number theorem in its full form, we define certain corresponding functions. So first of all, we define small l of m as log n if n is prime 0 else. Then we define the von Mangold function lambda as log p if n is of the form p to the power k with p some prime 0 otherwise. Now we need some more notation to fully understand the prime number theorem. So for notation we introduce deco of a function f of x is said to be g of x if there exists some constant c such that this of g of x is such that constant times f of x. We introduce small a of f of x equal to g of x if x tending to infinity gx by fx is equal to 0. Now, you see, we introduce another notation. We call it asymptotically equal. So f is said to be asymptotic to g if limit x tending to infinity fx by gx is 1. So what is this? So using this notation, we'll be using this notation a lot. So keep it at the back of your mind. And as for form the prime number theorem, it says that phi of x is asymptotic to x by log x. So this is what we eventually want to prove by the end of this talk. Now, as a starting point, we'll be assuming from some results from analytic number theory. First of which will be Chebyshev theorem. Let me state it real quick. Chebyshev theorem. So before I state, I further define two new functions using these two functions that I just defined here. We define theta of n as summation n less than equal to x of n of n, and I define psi of n as summation n less x less than equal to n x less than equal to n x. Now that I have defined these two new functions, theta and psi, I can state Chebyshev's theorem, which is essentially saying that there exist constants a and b such that a is less than equal to theta of x by x is less than equal to psi of x by x plus less than equal to pi x log x by x is less than equal to b, and limit. So this is the notation for limit, which is limit infima. Limit of theta x by x is equal to limit in psi x by x is equal to limit pi x log x by x, which is strictly less than log 4. Similarly, I can make a similar statement considering lim subs. Oh my god, this should be, it's not log 2, my god, this is greater than log 2. For lim sub, we have lim sub of this thing equal to lim sub again of this thing and lim sub of this thing. This thing is bounded above by log 2. Yeah, so this was, so the lim ints are bounded below by log 2 and the lim subs are bounded above by log 4. This is what Chebyshev's theorem tells us. Next up, we have a few more results from analytic number theory. Now, these results might seem like random at first, but we need all of it. We need somewhere to start, and we use these results as a starting point. And each of these results individually is pretty straightforward, have pretty straightforward proof. So, begin by stating let f be unimodal. Unimodal means it has local maxima is interval 1 to infinity, and let's say f is integrable. Then we define capital F of x as summation n less than equal to x of fn, and this thing for unimodal functions, this identity holds t plus 1. So if you have a unimodal function, you can approximate the summation of that unimodal function by its integral. That's what it said. Added some constant, like the error term is of the order of a constant. That's what it says. Using this, it's pretty easy to see. Like from here, you can reduce that summation log n less than equal to x should follow x log x minus x plus order log x. We can reduce it from this level here. Next up, we have something called double counting. It basically says that if you have an arithmetic function f of capital F of x defined as x n less than equal to summation fx, then you can say that if you want to evaluate this summation, if you want to find out this particular summation, then this particular summation, you have two ways of finding this out. You have summation e less than equal to s f g times gif of x by t, gif, the greatest integer function, and at the same time, you can write this as n is equal to x, where n is an integer, d dividing n of f of g. So the face, from here you can clearly see that this is in fact double counting in a different way. This is in fact double counting. Now that we are done presenting this, I'll move on to another result from analytic number theorem. Before that, I'll have to erase this board. That in a minute. Using this particular double counting theorem, let me just start all the theorems that we problems. Using this particular double counting theorem, you can see that summation. So let me say from double counting theorem, summation n less than equal to x psi of x by m is in fact, now remember, when we define psi as the sum of the one-manifold function. So here we can easily apply the double counting theorem and see that this is in fact equal to lambda d lambda of t times the of x by d, and this is in fact equal to h log x minus x plus o log x. Now, as a hint, this comes from the fact that lambda d from Chebyshev's theorem, you know that lambda d is in fact of the order of x. So, as right here, as a conclusion of Chebyshev's theorem, we can deduce that lambda x is of the order of x psi of x. Sorry, my bad, not this. What was it? Theta. As a consequence, theta of x is of the order of x. Psi of x is of the order of x, and phi of x is of the order of x by log x. Now why is this x by log x? Because pi of x multiplied by log x is of the order of x. So when you take the log x here, it becomes order of x by log x. And from this particular conclusion, you can clearly see that there are three equivalent formulations to the prime number theorem. We had the original formulation here, but we can write two equivalent statements from Chebyshev's theorem. We can further conclude that the prime number theorem is equivalent to showing that psi of x is asymptotic to x, or you can likewise show that theta of x is asymptotic to x. So, and I'll write it formally as this: the following are equivalent. This, and this. So we have three equivalent statements, which is a conclusion of Chebyshev's theorem. Now that we have this, we can use this further. Again, I am not deriving it, but it's what we use to derive something called Merton's theorem. Which tells us that summation log p by p, where p is a prime less than equal to x, is equal to log x plus something of the order of 1, and summation lambda n, where lambda is a one-manifold function, n less than equal to x is equal to log of x plus something of the order of 1. Now that we have Merton's theorem, we are almost done laying the groundwork. We just need a couple of more results. I'll state another one here. From Merton's theorem, we can deduce that theta of n by n square, where n is an integer less than equal to x, this has the order of log x plus something of the order of 1, and eventually, yeah, I'll need some things here. So I'll erase this. We write down one final result called the partial summation. Partial summation. What is this? This tells us that if you have two arithmetic functions f and g, and let's say you have g to be continuously differentiable, then summation n less than equal to x, where n is an integer, this is going from, we evaluate fn times gn, then this sum is in fact equal to some capital F, which we define in a moment, capital F x g x minus the integral from 1 to x, capital F x g dash. So this is where, this is with t. The variable of integration here is t. So this is where g being continuously differentiable comes into play, and here capital F of x is in fact summation n less than equal to x of small f of x. So this is the partial summation formula, and using the partial summation formula in various ways you can derive a multitude of useful results, 4 of which we need right now, but there are many of them. First one being summation. This is a very famous one, 1 by n. So summation n less than equal to s of 1 by n is equal to log x plus some constant gamma, which is a very famous constant, plus some remainder r of x, such that this r of x satisfies the property mod of r of x is less than 1 by x. Then we have another result, that summation n less than equal to x log square n is equal to x log square x minus 2x log x plus 2x plus order of log square x. This is our second result. The third one is summation n less than equal to x log square x by n is equal to 2x plus order of log square x. This is almost done. One final result that we need is, again, this is a combination of this result here is a combination of two theorems. I don't think this will be visible, so I'll write it on the other. This is final result that we need, that summation ud by d less than equal to x is of the order of 1, where mu is Mobius function. Alright, we know what the Mobius function is. Now we have done laying the groundwork for our eventual line of attack. So what we are going to do, we are going to analyze something called generalized von Mangold functions, and using generalized von Mangold function we'll use something called Selberg's formula. The Selberg's formula, he gave 3 variations of it, and using those 3 particular variations he gave a proof which, like, as you see, the proof is quite beautiful. So, to formally state what a generalized non-manifold function is, first of all, we need something called a convolution. The convolution of two arithmetic functions is denoted by star, f star g of n. This is defined as d, where n is an integer, remember? F d times g of n by d. This is what a convolution is. Sometimes it's called a Dirichlet or D. And then define the function capital L of n simply as log n. So this function is basically log n for all values, for all numbers n. This function is log n. So we're going to show that first of all we define generalized non-manifold function denoted by lambda subscript r of n. It's defined as mu convoluted with L to the power r, where L is this function, capital L. Alright. Now our object of interest will be lambda 2. So lambda 2 of n, what should it be? It will simply be mu star L square. Now mu star L square is our object of interest right now, and you can see that mu. So it's not a very difficult thing to see that mu star L square would be in fact lambda n. So basically denoting representing lambda 2 in terms of lambda. Plus lambda convoluted with lambda of n. So this is one of the identities that we are going to use going forward. This will be very useful. I'll give you a hint for the idea behind this proof is the function L acts as something called a derivation, something like a derivative only on the ring of arithmetic functions. So if you have two functions f and g that are getting convoluted, so L multiplied, this dot is multiplication, normal multiplication, L of f convolution with g is in fact L multiplied by f convoluted with g plus f convoluted with n multiplied by g. This is something called a derivation on the ring of arithmetic function, and using that you can easily show this identity. We state it right now for the time being without this. Alright. So we have identified our object of interest and we are going to analyze it even further. I present to you Selberg's formula. What is Selberg's formula? Selberg's formula tells you that summation n less than equal to x, lambda 2 of n is in fact 2x log x plus something of the order of x. Now this the formula right there, it is what is at the heart of Selberg's proof. So, and proving this would require all of the stuff that we have been presenting so far, and proof is quite long, so I'll clear the board in advance for that. thing involves using the identity that we had written on that board before coming here. So we directly write this as, first we use the definition that lambda 2 of n is basically u convoluted with L square of n. This is in fact because let's say you have some number d less than equal to x, is mu d times normal multiplication log squared n by d, and now we can like replace this index n by d and instead we can write some k, and here we can replace this d by kd. So this summation runs over all kd's that are less than equal to s, and we are summing ud with log square of k. Right, that is a bit more easy. Now we can simply take this summation, we can make it a composition of summations, so to speak. We sum right d less than equal to x, mu d multiplied by summation, so this is like the inside term, k less than equal to x by d log squared k. Now this is where the formula that we give for the order of log squared k comes in place. We recall that the formula for the order of log squared k, I'll write it down once again. We recall summation log squared n less than equal to x, or in fact x log squared x minus 2x log x plus 2x plus something of the order of log squared x. This was the formula that we found out when didn't find out, but we are going to use this formula and substitute it in here to find out our expression. So, but before we do that, we are going to arrange it, we are going to organize it a little bit so that we don't have to deal with so many terms. So if you look at it closely, see these are like 4 distinct terms, and each of these terms will be eventually get multiplied by mu d on the outside, and here the x will be replaced by x by d because we are summing till x by d. So that should be explanatory. So first we look at the term. Let's look at something like this. See, log squared x is always less than some constant function, so not constant, like it's always less than this thing. Let me write it out. Write out the terms as such. And first combine these two and write mu d times x by d log x by d multiplied by log x by d minus 2, because I combine those two together. So this is our first term. The second term, would be 2x times mu d by d less than equal to x, and the last term would be simply t. So we remember that ud was, whenever you have this mu d less than equal to x, mu can have the value of -1, +1 or 0. So this function is of the order of x, right? That means when you eventually multiply it by log squared x, you get something which is of the order of x itself. And now this term, the one I am highlighting right now, the summation ud by d term. This summation ud by d term, if you recall by Morton's theorem, this term has the order of 1. So I can ignore it, and when it gets multiplied by the 2x here, this combined term becomes something of the order of x. So I have something of the order of x and something of the order of x. These two terms combined to give me something of the order of x again. This simplifies two terms. Now we are left with this gigantic term. So I will leave this term on the next board. So I'll rewrite the term. So right now I'll just write the whole thing out first. D less than equal to x equal to summation whatever that term was. So that term will be D less than equal to x u d x by d times log of x by d times log of x by d minus 2 plus something of the order of x which we deduced from the previous book. Now what we'll do is, we remember from this particular result that summation 1 by n less than equal to x is in fact log x plus some constant gamma plus some remainder of the order 1 by x. So we invert this, so we substitute log x from here and we will substitute in here and write this particular thing as summation 1 by m less than equal to x by d minus gamma minus 2 because 2 is also there plus something of the order of 1 by x. Correct? So not 1 by x. So it will be d by x because here we are replacing the x in here by x by d. So this thing becomes order of x by d. So what we are basically left with now is summation d less than equal to x u d, I'll remove x here, u d by d log x by d times summation 1 by m, where m is less than equal to x by d minus, I am combining this and calling it c, and so it's not very clear that I am just erasing this step here because it's obvious what I am doing in the second step. This is some constant c plus this is something of the order of b by x. Again we start comparing terms and see that, see, if I write this out like this, if I am analyzing each of these terms individually, then you can see that first term is, like after rearranging it, it becomes, so I have d here, I have log x by d here. So what does it become? It becomes mu of d by d, and now I'm taking log of x by d. But instead of x by d, what I'm going to do is, I'm instead going to write it as such, log x minus log d, and then you can see that if I take the log x out, then this becomes mu d by d, and mu d by d by Watson's theorem, I can easily recall that the order of summation mu d by d was something of the order of 1. So this first term will give me something of the order x because I have an x outside it. So let me just write it out now. This is the first term, and this is my second term. This is the second term. C, x is outside, and we have summation, and c is also outside. D by d log x by d plus, see, when you multiply order of d by x by this thing, then this thing just like this d and this d, they get cancelled. You are left with something of the order of 1 by x and something of the order of 1 by x, and here you are doing mu d times log of x by d. By the same logic, you can see that, see, if you split it out again, log x by d becomes log x minus log d, so you get this thing again, and when you get this thing, for the first one, you can take, because this time the d would have gotten cancelled by this d up here, so that's why you are simply left with x log x multiplied by the summation of mu d, which has the order of 0, and next up you have the second term, which is the order of the second term will be x times summation b less than or equal to x minus mu d log d. So, and like it was a result that I forgot to mention that lambda is in fact equal to minus summation minus d log t. This is something that I forgot to mention. I should have mentioned it earlier. And using that, you can simply see that, so that would be of the order of lambda, and since summation lambda is of the order of x, then this thing should be of the similar order. So what do I have here? We have something of the order of x left out over here. After I did this and then applied that to get something of the order of x. Then I can further resolve this as x summation b less than equal to, sorry, so I switch it to n where n is an integer, n summation b dividing n ud log x by b. This is just the first term that we are looking at, and the second term is this. This I can, so c times x, and this stays the same. So for this one again, we'll have to analyze these two terms separately. But for this one, I am stating without proof that this is of the form order of 1. Again, the logic is similar because you have x and here an x. Like you have log x up top, you take it, split it up like this with log x outside, ud by d is of the order of 1, and you get, for the second term, you get ud log d divided by d. Ud log d has the order of this, and you are dividing it by d, so its order must be less than that. Get order of 1 from there. For this one, on the other hand, what you can do is you can read like what we did here, we do here again. We do that and we get something like where did it go? X summation. Wait, let me just print it out first. X log x summation n less than equal to. So this term right now, this term was order of 1. So when it's multiplied with cx, it becomes something of the order of x. And this term right here, now when b divides n, if you take the log x term, the log x comes out and you simply ud d divides n. Now this thing is 0 for all n greater than 1. This term becomes 0. On the residual term, what do we get? We get minus x summation n less than equal to x 1 by n summation d dividing n mu d log t. And by what I just said here, this whole thing with the minus inside, this whole thing is nothing but lambda of n by this, which I forgot to state earlier. So so this is 0 for all n except 1. So the only thing that's left out from here is a 1, because the inside term becomes 0 for all integers n other than 1, and only for n is equal to 1. It's a 1 left here, it's a 1 here, so you will get a 1 here. At least our result should look like less than equal to x. Lambda 2 of d, you had x log x from there, and you had something like x times 1 by n less than equal to x lambda n. Now by Burton's theorem, if we remember that this thing was log x plus something of the order of 1, that means this whole thing will be 2x log x plus something of the order of x. And we're done with the proof of Selberg's formula. So this was a very long and convoluted proof, but ultimately we show that this particular identity, so to say, Holstrom. Using this, we'll give three equivalent formulae, which are called Selberg's formulae, ironically. And these Selberg's formulae will eventually help us in. So each of these Selberg's formulae by itself, it's not that important, but these are more like cases that you need to consider when you're finally proving the prime number theorem, when you're constructing the proof for prime number theorem. So for that, yeah, again I need to erase the board for that before I see three formulas that I intend to show. This one written here. Look at this one written here for reference. Alright, so we begin with defining some new notation. Define summation PQ less than equal to X, where P and Q are both primes. It is defined as the sum of all ordered pairs. The sum is running across all ordered pairs P, comma Q, where P and Q are primes, and the product is less than equal to X. So it's defined as this. For example, consider say if you have like X is equal to let's say 6, then you have consider all the ordered pairs primes so that PQ is less than 6. In fact, there's only one, so that's not a good example. Let's say 8. You have 2, 2. You have 2, 3. You have 3, 2, and that's all. So your summation would be log 2 squared plus 2 times log 2 log 3. This is what summation PQ less than equal to 8 of log 3 log Q with U. This is just some new notation we are defining. Just the example. And state equivalent of this is another, basically a theorem due to Selberg. Let's call it Selberg. So there are three formulas. One, summation log squared P, which is equal to X. P is a prime, by the way. Q less than equal to X. Log P log Q is equal to 2x log X plus something of the order of X. This is the first one. The second one is define theta quite some time ago now. Theta x log X plus summation log P theta of X by P less than equal to X is again equal to this thing only, 2x log X plus something of the order of X. And third one is summation log P less than equal to X plus summation summation EQ less than equal to x log P log Q by log EQ is equal to 2x plus something of the order of x by 1 plus log x. So there are three formulas in this theorem, and we have to show that each one of them is true. So most of it is algebra and some arguments from analytic algebra, of course, but the essence is that we get to show various things to be true when we are eventually constructing the proof for the prime number theorem. And for that, for proving each of this, you have to start from there. So I start from here. I have summation n less than equal to x. So this thing, what was this thing? I found this out to be equal to multiplication of these two lambda times L of n plus summation. So I'm just breaking this summation down. Lambda convoluted with of n. Alright. And now we evaluate each one of these terms individually. So you can see that this term, so capital L was simply log n. So this term right here, this term is equal to summation p less than equal to x log squared p. P is a prime. Remember, when p is a prime, lambda is simply log p, and this is log p for everything. So this is log squared p, and where this thing is some prime power less than equal to x, and the prime power exponent should be greater than equal to 2. In that case, this thing becomes k times log squared p. Well, k times log squared p works for this too, but we wanted to separate this out. We'll see why in a moment. Now we look at this term. See, this term is a desired term. Why? Because we have it involved in this formula right here. So that's why we somehow want to get rid of the k log squared p term. We get rid of it and we'll show that this thing has the order of O of x. So for that, you can simply see that this particular, I'll write it down here. This summation right here, let's just denote it S for simplicity's sake. S is in fact equal to, so whenever you have a prime that has an exponent k, like if you have p to the power k less than equal to x and k is greater than equal to 2, then p must be a prime that is less than equal to root x. And by that, you can simply say that p, this summation S is in fact equal to p less than equal to root x log squared p times summation k going from 2 to GIF of log to the base p of x, and you are summing k over it. This basically sums all those times where you have an exponent of p which is less than x. Now this particular term right here, which I am enclosing in the box right now, this particular term will be less than equal to log x by log p whole squared. So that means S as a whole will be less than log squared x times summation p less than equal to root x 1, which is simply less than equal to root x log squared x will of the order of x. That means this whole thing is of the order of x, and what we have eventually deduced is that the first term right here, that is, I'll write it here. The first term, which was lambda dot L summation n less than equal to x, lambda dot L is in fact OX summation log squared p x plus something of the order of x. This is done. Now for the second part, we'll look at this thing. at summation n less than equal to x and a convolution with lambda, then this thing will be equal to, see, whenever you have something that has more than 2 prime factors, then this convolution is by default 0. And because for lambda of n to be non-zero, you need it to be the power of only exactly one prime number. So that's why if you have more than 2 prime divisors of n, you get 0. So that doesn't count. So that means this sum is essentially running over all those p, k, q, l less than equal to x. These are all the numbers that have at max 2 prime distinct prime factors. This would be log p, log q. Now again we separate it out into two summations. Separate it out into those summations which have pq less than equal to x, log p, log q, and we separate it out into those summations where at least one out of k and l is 2 or above. So that would become p, k, q, l less than equal to x, and k plus l greater than equal to p, and both individually are greater than equal to 1. Same thing here, log p, log q. Now this particular summation, I'll just write it. This particular summation right here, this summation will be less than equal to the case where, so it would be less than, in fact, 2 times the case. I just, by the 2 term here, just came in a moment with symmetry. Just write it down. Of q. So basically, instead of letting the sum be greater than equal to 3, I'm just letting, here I am fixing one of them to be strictly greater than equal, no, not strictly. One of them is being fixed to be greater than equal to 2, the other one is getting fixed to be greater than equal to 1. So in essence I am overcounting. That would be E, K, Q, L less than equal to x, K greater than equal to 2, L greater than equal to 1. The mirror case would be L greater than equal to 2, K greater than equal to 1, and since both of them are symmetric, both of them are equal, and why is this greater than this? Because we are overcounting. We are counting those cases twice. And this particular thing, well, for this particular sum will be 2 times summation log p, k less than equal to x, k greater than equal to 2, and here on the inside we have log q to the power l less than equal to x by p to the power k, l greater than equal to 1. Now this particular thing, if you look at it, what is it doing? It is just summing log q, where whenever q to the power l is less than x by p to the power k. What is this? This is a function psi of x by p to the power k. By the definition of psi itself, this function is this summation is in fact equal to psi of x by p to the power k by the definition of psi. So if we rearrange it a little bit, write it down, and we remember that by Chebyshev's theorem, we remember that this is bounded above by x. So there exists a constant such that I can write the following. Just erase it and rewrite it here like this. So right now I showed that the inner summation is just psi of x, and I used the fact that psi of x, so here we were dealing with psi of x by p to the power k, and that thing would be bounded above by x by p to the power k for some, this would be 2. See, there is a constant c such that this is less than equal to c by p to the x times xc by p to the power k. So what does this mean? This means that this whole summation right here, let's call this summation t. This summation t is of the order summation. So I replaced psi of x by p to the power k by x by p. I can write this as order of x by p to the power k by Chebyshev's theorem, and I'll get log p x by p to the power k, where p to the power k is less than equal to x and k is greater than equal to 2. Now I have to analyze this sum. For this sum, I'll just force to read. Like I can take the x outside this summation. I can look at this summation. So this summation, this particular summation right here, because we are dealing with the order, I can simply rewrite this as x times summation p less than equal to x log p times summation 1 by 3 to the power k going from 2 to infinity. Clearly, this should be bounded over by this because this thing is clearly greater than what we had here to begin with. Now, this is simply a geometric progression, and we know the formula for the sum of a geometric progression. So, we can simply rewrite this as log p by p times p minus 1. And since this is a convergent sequence, you can check it by integration test. This is a convergent sequence. Log p by it's bounded above by a convergent sequence, thus it too must be convergent. So at the end of the day, this is bounded above by a constant, and thus this whole order function is nothing but order of x. So what I had just shown is that out of the like this thing, what I have just shown is that this thing has the order of x. So now that I have shown this, I have basically shown that. I've basically shown that. So we began with lambda 2. And remember, lambda 2 had the order, and it was 2x log x plus something of the order of x. And when we split it out into lambda dot L and lambda convolution with lambda, then we show that we had summation log squared. I'm not writing the indices because it's clear at this point. Plus summation log p log q. Now this thing was in fact something plus order of x. It was here, and this thing was second term too. The convolution term was also the main term plus something of the order of x. So in essence, order of x, you have one order of x here and two order of x functions here. When you take their difference, the resulting function will also have the order of x. So that means 2x log x is equal to summation log squared p plus summation pq less than, just avoid index, log p log q. And here you have the first one. The first of these three formulas is thereby done. Now, to prove the second formula, I will not go into the detailed proof, but I just mentioned a key insight for that. First formula is like almost directly derived from the second formula. Just need to observe a couple of these. See, recall that for a unimodal function, you can define summation fx as, like if you define it as some capital F of x, then capital F of x will in fact be integral from 1 to x of small f t dt plus something of the order of 1. This was a unimodal function, which means it has a local maximum. We looked at this. So using this, you can see that summation log square p less than equal to x is in fact theta x log x plus something of the order of x. This is the order. I'll get to it later. But the first key insight is this, and then what you can do is, this is like the first key insight that I have underlined. Second key insight is log p log q is in fact this is the same summation, equal less than equal to x log p log q. When you rewrite it like we did while dealing with it, you can rewrite this as p less than equal to x log p multiplied by theta of x by p, because why is this true? When we take this summation inside, we are basically doing q less than equal to x by p summation of log q, which is by definition equal to theta of x by p. So from there you can clearly see that this thing holds. And now when you substitute these two results into the first formula, when you substitute these two into one, then you get that what? You get that theta x log x plus something of the order of x plus summation log p theta x by p. This is in fact equal to, by the result of the first formula, this is equal to 2x log x plus something of the order of x. So the order of x things, like the difference of two order of x functions is another order of x function. So hereby you have the second formula. Using these two insights and by using the first formula, you can easily get the second formula. Next up, we have the third formula that we have written on that board here, and these two formulas go on to that. So for this one, what we need to do is we need to look at a function f of n defined as small l. Remember, small l of n was log n if n was a prime, 0 otherwise. Small l of n is log n plus l star l of n. Then we define capital F of x as summation n less than equal to x of f of n. Then you basically get summation ln log n plus l star l of n. Now, from here, you can see that this thing, the first term for any prime p, this term will be log squared p, and like for any other natural number, and it would be 0. And this particular term, this is convolution. So if you have any number that has, let's say, more than 2 prime factors, it would be 0 for that. So this term will only consist of those numbers pq that are dividing n. And since this n is an integer less than equal to x, this summation, so if I split the summation into two parts, I can write it as summation p less than equal to x, because this is log squared p for all primes less than equal to p or less than equal to x. This term becomes log squared p, and the second term will give me log p log q. And what is this? This is just the first Selberg formula. So I know the order of this thing is 2x log x plus 1. I am not writing it here for now. But for now, you have just keeping it in mind that if I define small f as ln log n plus l star l of n, then the summation of f n over all n less than equal to x will have this order 2x log x plus something of the order of x. So I'm just directly writing out the result here. This thing would be 2x log x plus something of the order of x. Next, like so if you have, let's say we want to link with this thing now. So to link with this thing, we have to look at summation log p less than or equal to x plus summation p less than or equal to x log p times log q by log of pq. Now, if you look at it closely, if you let n be a number less than or equal to x, then these two summations are in fact, what is this? What will this be? This will be just be ln. The upper term right over there, it will come from L star L of n divided by log n. So the same logic that I presented to analyze the function for order of f. So, and now I can just rewrite this as summation n less than or equal to x, small f, where f is defined up here, f is defined up here, which is small f of n divided by log n. And clearly, since 1 is not a prime, so you can like tweak with the limits over here, and we can. So here we can use something that we use partial summation. We call partial summation as partial summation, where g was assumed to be a continuously differentiable function. So here we take g as 1 by log n. Clearly this is continuously differentiable. We can use this partial summation formula in our case to like resolve our problem. Using the partial summation formula, it gives us, see, f is treated the same as the f here, and g of n is in fact 1 by log n. So some easy computation gives us this is log x, and the minus sign vanishes when we take the derivative of 1 by log n. That would give you 1 by t square f, capital F of t by log square t dt. And this integral is from. So remember, for 1 this is undefined. So we need to take n strictly greater than 1 here, and that's infinite. This integral goes from, and since n is an integer, it goes from 2 to x. And now this thing, the capital F, you know that capital F of x is equal to 2x log x plus something of the order of x. So when you divide by log x, you get 2x plus something of the order of x by log x, because we're dividing by log x here. And this whole integral, here also you can like just substitute, instead of f up top, what you can do is you can substitute instead of, so we are dealing with f of t, the integral of f of t by this thing, we substitute 2t log t plus something of the order of t. Now this thing, the first term is simply what? It cancels out with this, not this way. So just do the cancellation. T log square t log square t. Now this gets cancelled, this gets integral of 2 by log t, it's something of the order of it's something of the order of it should be less than something of the order of x by log x, and at the same time this thing, because see 1 by log t when you integrate it, at best this is always less than 1, right? So you will always get something which is of the order of something which has less order than x by log x. So this integral basically gets assimilated into the order of x by log x now. And similarly for this you get like order of 1 divided by you get some function which has the order of t divided by t log square t. The t and t gets kind of cancelled to give you something of the order of 1 divided by log square t, and then you integrate 1 by log square t to get something of the order of 1 by log square t, and then again it gets assimilated into this particular order of x by log x term. So at the end what you're left with is just this. Now this is not exactly what we wanted. We wanted this x by 1 plus log x. So to see that, you can just see that x by log x is less than equal to 2x by 1 plus log x for all x greater than e, and for all x less than, the only case when x is less than e, when x is less than e, the only integer there is 2, and that's a negligible case. So you can directly say that this thing, because see, even though these the individual x by 1 plus log x term is not always greater than this, this term multiplied by some constant is greater than equal to this, and order of x ignores the order idea ignores all these constants of multiplication. So you can directly write x by 1 plus log of x, and you're done proving the Selberg formula. So now we have the tools that we need to construct a proof of the prime number theorem. I'll erase these 3 formulas, and I'll start with let's even start with the proof of the prime number theorem. So proof of the prime number theorem does not directly show that pi of x is asymptotic to x by log x. In fact, it doesn't even deal with pi of x. Remember, we showed when we stated Chebyshev's theorem, we showed that by Chebyshev, as a consequence of Chebyshev's theorem, we have 3 equivalent formalisms, 3 equivalent ways of writing the prime number theorem. One was in terms of theta, another one was in terms of psi. So right now we are going to deal with the proof here deals with the formal. Let me just write it out. First, we define the function r of x as theta x minus x. So what we want to show is that, see, if we show that theta of x is asymptotic to x, then we'll be done, because as a consequence of Chebyshev's theorem, this is equivalent to the prime number theorem. So to show this, that this particular limit holds, we'll show that this particular limit has this is in fact small o of x. What does this mean? This means that limit x tending to infinity rx by x is equal to 0. This is what the small o means. You remember that. And of course, if this is true, then this elementary calculus to show that this is asymptotic to x, and you're done. So we need to show this. We're interested in showing this. So to do that, we won't proceed directly. We'll show that it's possible to construct. So let me state this idea here. The idea is to show that there exists sequence of numbers delta m and um such that limit m tending to infinity of delta m is equal to 0. This limit should hold true for this. So and delta m is greater than delta. So delta m should be a decreasing sequence. strictly decreasing sequence, and the limit of delta m should be 0, and mod of Rx is less than delta m multiplied by x for all x greater than equal to um. What does this mean? For large, this is equivalent to saying if you make x large enough, you will get the ratio. See, take x here. The ratio Rx by x becomes smaller. So what does this mean? Like as a consequence of this, you get that if such sequences exist, then you are done, because this will hold true, and Rx by x will have its limit tending to 0, and you have the prime number theorem. So we just need to show that there exist such sequences delta m and um such that limit delta m tends to 0 holds true, and the modulus of Rx is strictly less than delta mx for all x large enough, that is greater than equal to um. This is the idea. This is the idea of the proof. So how do we show this? So we begin by taking a lemma. Let's call it lemma 1. We'll show that for x greater than p, summation p less than equal to x log p by p times 1 plus log of x by p. Yeah. When you're summing over all p less than equal to x, this summation is of the order log x. This is composition of functions, log of x. This is what we want to show. So now this is a pretty straightforward proof. Proving lemma 1 is as follows. See, by Merton's theorem, you know that summation log p by p is equal to log x plus something of the order of 1. That means if you have some x by, let's say, x by some e to the power j, if p belongs to this interval, and so if you have p belonging to the interval x by e to the power j and x by e to the power j minus 1, if p belongs to this interval, then this summation log p by p, this will have, well, you just take the difference. So this will be log of x by e to the power j minus 1 minus log of x by e to the power j plus something of the order of 1 minus something of the order of 1 as well, but the difference of two functions whose order is 1 is again something whose order is 1. This 1 is basically a constant now, and this thing, you simply see that this is 1. I mean, you take the ratio of these two, you get log e, and log e is constant. So this is of the order of 1, of course, order of constant. So now that we have this, also if p belongs to this interval, it's not difficult to see that j is less than equal to 1 plus log of x by p, this should be less than j plus 1. This is just reversing the inequalities and analyzing the bounds for j. So j belongs to this interval. Write this properly. So I have the bounds for j, and so if I have summation, so I can, instead of looking at the whole summation directly, I can just look at this summation in intervals of x. So I can break it down into two summations. So what would be this summation? X by power j minus 1 x by e to the power j log p divided by p 1 plus log x by p. This is what we began with. And now if I analyze this summation in parts, like I have divided the interval of 1 to x into these smaller intervals, and I'm looking at primes in these smaller intervals, then this is simply less than equal to 1 by j times x by p to the power j. Like again the same bound, so I'm not mentioning the bound here, I just call it, let's say these are, p belongs to some interval I j. This is the interval I j. So this becomes summation. Is less than equal to 1 by j p belonging to interval I j, where I j was defined as such here, log p by p. Again, this is trivial. This stuff here is trivial. And this, because this thing in an interval, we just showed that this thing, when it belongs to this summation is of the order of 1, then this thing must have the order of 1 by j. So, in each interval, this thing has the order of 1 by j. When you look at the summation as a whole, what do you have? You have, I'll just write it a bit smaller, use the rest of the board here. So this thing will have the order of 1 by j. Oh, by the way, if anyone is confused where the 1 by j comes from, just flip this, you will see where the 1 by j is coming from. So you have summation, summation p less than equal to x of log p by p 1 plus log x by p. Now instead of when we break down this interval 1 to x into these subintervals, how many of them will be there? There will be natural log of x, gif of that, gif of log x plus 1. That many intervals will be there, which is basically what? Which is basically the same as saying this is bounded above by summation j going from, because this was order of 1 by j. So when you sum all these j's, j goes from 1 to gif of log x plus 1. That is how many intervals, that is how many j's you can with. And we remember what was the formula for summation 1 by, like for 1 by j's you remember that it's same as log x plus gamma plus remainder of the order 1 by x. This basically gives you something like log of gif of log of this thing, log of, so I'll write it neatly. This will give you something like this, log of x plus 1. This whole thing is in log plus the other master plus something. This whole thing will be, I hope this is clear. And from here, you can say that you can ignore all of this term and just write this thing is bounded above by log of x. And we're done. We're done proving lemma 1. Now, using lemma 1, we'll prove something about the function r that we defined here, the difference function that we defined here. So I'll keep lemma 1 written here and I'll erase this side of the board. So we have something important, something theorem, theorem. It's a consequence of lemma 1, so we'll call it theorem 1. So theorem 1 tells me that mod of Rx is less than equal to 1 by log x summation n less than equal to x r x by n summation, so not summation, order of x log of x divided by log of x, lot of logs. So for proving this involves using Selberg's formula. Remember, the second Selberg formula was related with second Selberg formula told us that there is a relation between second Selberg formula told us between a relation in theta and the function 2x log x plus something of the order of x. So using that, we'll show that the function r has an upper bound that looks something like this, which is again in terms of r, but this bound can be resolved further. So all that 2x log x plus order of x was theta x log x plus summation p less than equal to x log p theta of x by p. Now if we substitute theta x as rx plus x upon substitution, just substitute and do the algebra, you will see that rx log x is equal to minus summation p less than equal to x r of x by p log p plus something of the order of x. Alright, this is just from substituting theta x as rx plus x. Alright, now we'll do something interesting. We'll keep this at the back of our mind. Let's say it's abstract, and we'll use it later. We'll use it when we derive another expression, similar expression for rx log x. For that, look at the summation q less than equal to x by p log 2 plus summation 2r less than equal to x by p log. This is basically the Selberg first formula. Instead of x, I am writing x by p log r log 2r is equal to 2x by p plus something of the order of. This comes from third Selberg formula. It was for the third Selberg formula. It was x by 1 plus log x. Instead of x, we are substituting x by p. So here we have x by p times 1 plus log of x by p. Now immediately when I write this, your mind should go to this lemma that we proved, where it had something to do with this order term right here. And indeed it has, that's why I wrote it in the first place. Now, look at this thing. Now, e log 2 is equal to summation. Well, in fact, instead of writing it like this, you can write it like this. You can write it as 2x summation log p by p minus summation p r plus x log p log 2 log r summation. Now what I did here, I basically used this formula and substituted it in here. So what I basically got was, I basically did what? I rewrote this as summation p less than equal to x log p times summation q less than equal to x by p log q. And then I moved this term over here and I substituted the log q, this summation for log q into here. This is what I get on the right hand side. And this would be some derivative term. So I'll just write it out. Log p by p plus log x by p. So now that I have this, I can use my lemma and see that this particular summation has the order of log x. So I can directly say that by my lemma, this thing is simply, this thing is nothing but the order of x log of x. So one term is taken care of. So these two terms, remember by Merton's formula, this thing was log x plus something of the order of 1. So when you multiply it by 2x, you get 2x log x plus something of the order of x. But something of the order of x is less than something of the order of x log of x. So that it gets assimilated into this term. So we have taken care of two terms and we have gotten 2x log x plus something of the order of log of, so x times log of x minus summation qr less than equal to x log q log r by log qr. Now instead of writing the whole thing as p, see here get 3 primes p, q and r. So instead of writing it in this way, you can take the log p inside and impose the restriction that p is less than equal to x by qr. When you impose the restriction p is less than equal to x by qr, the entire summation log p thing simply becomes theta of x by qr. So we use the same old trick again and you see that this thing becomes theta of x by qr. Now once again we will use the fact that summation log squared p. So what did we have there? Log squared p. Inserting, see this was the formula for this product term, right? It was the formula for this product term. So when you insert it into the Selberg formula that we had to begin with, we get that log squared p is equal to summation log p log q theta of x by pq plus also but divided by log pq, where of course pq is less than equal to x, something of the order of x log x, x log of x. So now we can see we derive the result by proving Selberg's second formula that this thing is in fact, this is simply by the statement that I wrote down for unimodal functions. You can see that this thing is equal to theta x log x plus something of the order of x. This was true and I showed it how during my proof of the Selberg's second formula. And using this, you can simply plug it in here, get that Rx. So again, what we do is, whatever we have in terms of theta, we rewrite it in terms of Rx minus Rx plus x. So what we do here is we say Rx plus x log x is equal to whatever we had here. So log p log q by log of p cube, and then here you have r of x by p cube plus x by p cube, and this order term stays as it is. It stays as it is. Now, yeah, you have this, and then from here, like it's like manipulation. So now, let me write it out here. This term is of interest. This underlying term right here, this term becomes summation x times this term becomes x times summation. Like simply the x comes out and the p cube comes in the bottom. Log q by q log p cube. Now, and the r term, I ignore the r term for now, just deal with this term multiplied by x by p cube first. So when you do this, you see that this thing, you can show that this thing has order log x plus order log x. It's not that difficult because the half of it was done when we do Selberg's second formula. And from there you can see that using this, we state this now without proof. Using this, you can see that this whole expression right here will simply have the order x log x plus something of the order of x log x. That's one term. Now for the second term will be r of x by p cube multiplied by log p log q divided by log of p cube. There for that, with hashtag, here's hashtag 1 for now. See, you had on the left hand side that x log x, and here also you are getting x log x from one term, right? So you get from here you get rx, because the x log x get cancelled. Rx log x is again equal to something of the order of x log of x plus that thing. Summation log e log q by log q r of x by p cube. Alright, this is there. Now we combine this with hashtag. You see that we get a mean upper bound for r of x log x. So we do the algebra now. See that we start r of x log x in fact equal to summation, the upper one is equal to n less than equal to x small n of plus n contribution L with n divided by log n. This is just applying triangle inequality on the summation. You will see that this thing forms. Yes, this is multiplied by mod of r of x by n order of x log x. Now this thing we remember we used it for the proof of the third Selberg formula, and from there we remember that the order of this thing was 2x plus order of x by 1 plus log x. Remember this from the third Selberg formula. The order of this function right here, and it sums over all this. This has this order. So then, by partial summation, that not exactly partial summation, it will be rearrangement. You can see that this thing will be equal to well, I'll substitute this thing here for in case of this 2n plus order of n 1 plus or before that I'll state that if you have two functions, two down there like this. We have two functions, g, and they are getting multiplied. Then x equal to f g, the product evaluated at the upper bound minus f g evaluated at lower bound plus summation f times g n minus g n plus 1 n goes from lower bound to upper bound, and capital F is basically summation n less than equal to f. So using that over there, that's just a way of rearranging the sum. Using that here, so that this is equal to r of x by n minus r of n by 1. How if you analyze each of these terms individually, you see that the main term is this multiplied by these two. On these two, you can see that r of x by n minus r of n plus 1, which just by normal cancellation you can see that this is in fact equal to 2 times summation of r of x by n modulus of that minus 2 times gif of x summation r of not summation in fact r of mod of r of x by gif x, and this thing will have the order of x. So the first term will simply have the order of, not the order of, it will be simply r of x by n, and is less than equal to x. This summation plus something of the order of x because of this. And remember, r of x by x will have the order of 1 because x by gif is always like it at between 1 and 2, right? So we've seen that 2 times this summation n times mod of r of x by n minus mod of r of x by n plus 1 is equal to this whole thing right here. Now, you see, when you analyze each term, individually, the second term becomes like this, and then the first term becomes like this. And for the second term, you have to notice that r of xn, mod of r of xn minus mod of r of x by n plus 1 is strictly less than theta of x by n minus theta of x by n plus 1 plus x by n square. Now using this, you plug this in for the second term. For the second term, that would be O of n by 1 plus log n times mod of r of x by n minus mod of r of x by n plus 1. You multiply these two to see that their summation would be in fact less than n by 1 plus log n times theta of x by n minus theta of x by n plus 1 plus x times summation of 1 by n log n plus 1. Now simple exercise will show you that this entire summation 1 by n times 1 plus log n is of the order of log of x, and on the other hand this summation would be less than equal to theta x plus n going from 2 to x minus 1 of summation of 1 by 1 plus log n times theta of x by n, and this whole summation again is bounded above by x times something of the order of log of s by this exercise only, because theta is bounded above by x square, and this summation is clearly less than equal to this theta of x is less than equal to x by Chebyshev theorem. So therefore this entire term has the order of log of x. So we saw that the second term will have the order of x log of x. The first term will become 2 times the summation of mod of r of x by n plus something of the order of x, and this residual term, for this residual term you have to observe that r of x by gif of x is of the order of 1, because x by gif of x is between 1 and 2. So that's why this is something of the order of 1. This x by 1 plus log x term, this is of the order of x also, and when you add it with 2x, you are left with something of the order of x. So this whole term is something of the order of x, which is clearly less than equal, which is clearly of the order of log of x of, which is clearly less than equal to something of the order of x times log of x. So as a combined result, you can clearly state that 2 times mod of r of x and log of x is less than equal to twice of summation of mod of r of x by n plus order of x log of x, which allows us to write r of x mod of r of x is less than equal to 1 by log of x summation mod of r of x by n plus order of x log x by log x. And this is our second theorem. So this is our first theorem, and the second result that we need to prove Selberg's eventual theorem. Now we are going to state 2 lemmas, and in the interest of saving time, we are going to omit the proof of most 2 lemmas. But the first lemma is a direct application of the theorem that we just reduced, and the second lemma is a direct continuation of the first lemma that we are going to introduce going forward now. So I present to you lemma 2, which says that delta belong to the interval, open interval 0 to 1, then there exists some c naught greater than equal to 1, and there exists some x1 which depends on delta, that's why I am writing x1 of delta greater than equal to 4, such that if x is greater than equal to x1 of delta, then there exists integer L belonging to the interval x to e to the power c naught by delta of x and r of n is less than. So this is our first lemma that we are going to state, and as a direct consequence of this lemma, we are able to state lemma 3. This tells you that if you have some such a c naught greater than equal to 1, and this is the same c naught as you have in lemma 2, and delta again belongs to the open interval 0 to 1, and there exists some x2 of delta, where again x2 is a real number which depends on delta, such that if x is greater than equal to x2 of delta, then the interval x to e to the power c naught by delta of multiplied by x has a sub-interval of the form y times e to the power delta by 2y, such that strictly less than 4 times delta of t for all t belonging to this interval. That interval is this delta by 2 pi. So we have our two lemmas, and we use these two lemmas to give a proof of the prime number theorem. So what we will do now is basically we show using these two lemmas that theta x is asymptotic to x, and that will give us the prime number theorem. So, theorem theta x asymptotic to x proof. So by Chebyshev's theorem, we know that lim sup of theta of x is bounded above by log 4 and lim inf of theta of x is bounded below by log 2. So that tells us that lim sup of Rx is bounded above by log 4 minus 1, which is less than 0.4, and lim of Rx is bounded below by log 2 minus 1, which is greater than minus 0.4. So that means there exists some u1 such that mod of r of x is less than some delta 1 x for all x greater than or equal to 1, where delta 1 is equal to 0.4. Also, as a consequence of Chebyshev's theorem, you know that there exists some m such that mod of r of x is strictly less than mx for all x greater than or equal to 1. So Chebyshev's theorem gives us these two statements. Now we shall begin constructing our sequences. The delta 1 less than delta 2 less than, this is a decreasing sequence such that limit m tending to infinity delta m is eventually 0, and we link it with some other sequence epsilon m such that epsilon's limit m tending to infinity epsilon m is also 0. So we define our sequences as follows. Let us suppose we have some m greater than or equal to 1 and we want to pick epsilon m. Then we pick epsilon m such that 0 is greater than epsilon m is less than 1 by m. And if you have a delta n already picked up, so we have delta 1 already. Now we corresponding to delta 1 we can pick epsilon 1, corresponding to epsilon 1 we pick delta 2, corresponding to delta 2 we pick epsilon 2, and so on and so forth. We can construct our sequence. So if you have delta m, then how can you pick epsilon m? Epsilon m has to satisfy these two conditions. It also has to satisfy 1 plus epsilon m times 1 minus delta m squared by 256 c naught is less than 1, where c naught is the same number that appears in lemma 2 and 3. Alright, and you have to let delta m plus 1 is equal to 1 plus this thing times delta m. So 1 plus epsilon m times 1 minus delta square m by 256 c naught delta m. Now since this is by choice less than 1, then delta m plus 1 is strictly less than delta m, and that gives you a decreasing sequence. And you can clearly see that if epsilon m tends to 0, then as m tends to infinity, delta m is also forced to converge to 0. Alright, so if we are able to construct a sequence, so we are able to now construct our sequence. All we have to do is to show that our UMs exist such that mod of Rx is less than delta nx for all x greater than or equal to UM. All we want to do is to show the existence of this UM, which basically means for large enough x, your Rx is less than this delta mx, and this delta m tends to 0. That will tell you that the ratio mod of Rx to x will eventually tend to 0, and you will be done. So, to show that such a UM exists, let us assume that, let's say, you have UM. Then we proceed by induction and show that UM plus 1 also exists. So let delta dash be defined as delta m by a, where you already have delta m, you have the sequence of delta m and epsilons, and you have the existence of UM. Clearly the base case holds because U1 exists, and U1 will simply be the number for which delta 1 holds to be 0.4. So now suppose you have UM. So for constructing UM plus 1, first you let delta dash m be delta m by a, and let rho is equal to exponent e to the power c naught delta dash by m. Then if you have any x greater than or equal to some x3 of m, where x3 of m is defined as the max of x2 of delta dash m, where x2 of delta dash m is the same as we have defined in lemma 3, and the other quantity is um. So whenever you have x greater than or equal to this particular number x3 of m, which we have defined here, then by lemma 3 there always exists a sub-interval y 2 e to the power delta dash m by 2 by such that mod of r t is less than 4 times delta dash m t. Now from here you can see that if this is true for all t belonging to, so this is true for all t belonging to this interval. So if this is true for all t belonging to this interval, then you must have that rho to the power k must be less than or equal to x by x3 of n. But that would mean k is equal to delta m log x by c naught plus something of the order of 1. So now that we have this, then we can apply the theorem that we had proven once a few minutes ago, that mod of r of x is less than or equal to 1 by log of x summation mod of r of x by n plus, so remember what we had here was order of x, log of x divided by log x. Now this whole function, it's in fact small o of x, because if you take the limit of x log of x divided by log x and divided by x, and you take the limit x going to infinity, you end up with log of x divided by log of x as x tends to infinity. Simple application of L'Hopital's rule tells you that time limit is 0. That's why this thing right here becomes small o of x. Now some easy calculation here. So if you have this n less than or equal to x, you split this partition into two parts. You split this into n less than or equal to rho to the power k, where k is the highest exponent of rho, highest power of rho, that is less than or equal to x, and you split it into the second interval will look like this. Now for the second interval, you basically split the summation into two parts. For the second interval, you can clearly see that so 1 by root power k and less than equal to x, 1 by n. So now this thing right here, this thing is greater than x3, x by rho times x3 of m. So that's why when you apply the formula, you can see that this thing is less than equal to log of rho x3 of m plus something of the order of 1 by x. But these two things are constant. This is something of the order of 1, and this is of the order of 1, is less than something of the order of 1. This whole thing is of the order of 1. As for the second summation, what you can do is we split it into further subintervals. So you see, whenever n is less than equal to rho to the power k, and you have, so for that you have x by n greater than equal to x by rho to the power k, which is less than greater than equal to x3 of m, which in turn is greater than equal to um. So that means we are able to exploit the fact that mod of r of x by n is less than delta m x by n. So this implies that for any interval for all x, for all j, you have where j goes from 1 to k, you have x by rho to the power j and x by rho to the power k, which is in turn greater than equal to x2 delta dash m. By definition of x3 of m, you can see that this is true. So you can basically write that mod of r of t. So there exists a subinterval for every interval x by rho to the power j to x by rho to the power j minus 1, such that t for any t belonging to that subinterval, this inequality holds true. So that means you can rewrite the first summation part as summation. So for any interval, you can write x n belonging to rho to the power j minus 1 to rho to the power j r of x by n mod. Now this can be further split into two parts. The first part will be the subinterval for which this particular inequality will hold, and the second part would be that excluded part for which this inequality won't hold. Why is this inequality true? This inequality is true by lemma 3. So now when you have this, you can basically split it into two subintervals to get to the conclusion that this is in fact less than equal to delta m x times summation n less than equal to, this is n belonging to rho j minus 1 to rho to the power j 1 by n minus delta m x by 2 times summation of n belonging to ij, where ij is the subinterval in rho to the power j minus 1 to rho to the power j, such that this inequality goes true. I just denoting just that subinterval of the here. So you can see that this is true. And from here, then further, from here it's just direct calculation to show that it goes true. Now that we have that, what we do is we further analyze these two terms individually. So first we have to analyze delta n x and summation 1 by n belonging to the interval. Well, first we let n is equal to rho to the k, but this will be less than equal to delta n x log x plus something of the order of x, and for the second term what you can do is the second term. So when you have this delta n x constant for everything, it just comes out as a common, and you get this thing, and this thing is bounded above by delta m x log x plus something of the order of x. On the contrary, if you have summation 1 by n, where n belongs to that particular subinterval ij, if that inequality holds there is true, then this thing right here, let me just write out ij in this form right now, yj, comma, e to the power delta dash n by 2 yj 1 by n, then this thing is equal to delta dash m by 2 plus something of the order of 1 by yj, which is basically the same as saying something of the order of rho to the power j by x, because again yj is a subinterval, so this is a subinterval of x by rho to the power j minus 1 to x by rho to the power j to x by rho to the power j minus 1. Since y is subinterval, yj will, like, order of 1 by yj will always be less than the order of rho to the power j by x. Now you can see that summation j going from 1 to k of this thing. So summation n belonging to ij. Yeah, 1 by m is equal to, in fact, delta dash n k by 2 plus this summation will go from here to 1 to k. So that will just give you something of the order of summation rho to the power j by x, where j goes from 1 to k. Now this thing right here, we know the value for k. We know the value for k, so we will just substitute it in here. Delta dash m was defined as delta dash m was defined as delta m by 8, and so this thing right here, this rho, since rho was a constant to begin with, and this particular j going from 1 to k summation rho j by x is basically a sum of a leaf, which is basically of the order 1 by x, so it is bounded above by 1. That's why you can simply say that this thing is something of the order of 1, and this term particularly, when you substitute the values of k and delta dash m, this thing becomes delta square n times log of x times 128 c naught plus something of the order of 1. Alright, we are almost there now. So when you eventually multiply this summation by this delta m x by 2, you get that, and you combine all of the results that you had there, you get that summation n less than equal to rho to the power k mod of r of x by n is less than equal to something of the form. So we know that this particular term is bounded above by delta m x log x plus rho x. We write delta m x log x plus something of the order of x minus. So when you multiply the delta m by 2 here, you get delta cube m log x divided by 256 c naught plus something of the order of x. But this is in fact equal to delta m now that we have that, we can apply the theorem we proved earlier to see that mod of r of x is in fact less than equal to. So it was a 1 by log x term here, but you have another log x here, it gets cancelled, and left with 1 minus delta squared 256 C naught 256 C naught times delta m x plus. So remember, when we had something here, we had something of the order of small o of x, and you are dividing it again by log of x. Whatever is left out here is of the order small o of x again. Now that we have this, see, this function will eventually since this has its limit when divided by x equal to 0, there exists large n of x when eventually every linear function will outgrow this particular function. So that means there exists some un plus 1 such that order of x, this function, will be less than epsilon m and 1 minus delta square m by 256 C naught x, because this is a linear function and this function will eventually get outgrown by this particular function for all x greater than or equal to um plus 1. So we have shown the existence of um plus 1. So this implies that mod of r of x is strictly less than 1 plus epsilon m times 1 minus delta squared m by 256 C naught and delta m x. But this, what was this? This was delta m plus 1. So we have shown there exists um plus 1 such that mod of r of x is strictly less than delta m plus 1 x, and thus therefore we can say that theta, so we can first say that limit x tending to infinity r of x by alright r of x by x is in fact 1 okay. Oh, sorry, alright, is equal to 0. So this eventually means that theta of x is asymptotic to x, and this is equivalent to saying pi x is asymptotic to x by log x, and there you have it. You have the prime number theorem. It's done. So a quick note on the history of this proof. See, it was thought that elementary proof of the prime number theorem would give us great insight into the workings of the number, like the methods of number theory. But it so happens that the proof that Erdős and Selberg they both found, it so happened that it's a proof for the sake of an elementary proof. It did not give any further insight, that much insight as mathematicians expected that it would. But at the end of the day, it's a beautiful proof, and it's a proof that's worth studying just for the sake of it. I hope you all enjoyed the talk, and I hope to see you all in the next mathematics lecture. Thank you.
Any differences?
Melvin B. Nathanson. Yeah. So the references I would suggest would be an elementary. No, what was it? Oh, write it down. Yeah, so the references I would suggest would be an introduction to elementary methods in number theory by Melvin B. Nathanson. So I write it there. Melvin B. Nathanson. Elementary methods in number theory. This is in fact by itself it is a sufficient reference book for anything you want to study related to the prime number. It's elementary proof, that is. Elementary proof of the prime number theory. That will be done.
Any questions from the audience? If not, we thank our speaker once again.